Today we are going to discuss important points of Arrhenius theory. According to Arrhenius theory, reactant molecules collide each other to form a transition state or activated complex, which is then converted to product. It is the path of a chemical reaction. According to Arrhenius theory, reactant molecules collide each other to form a transition state or activated complex, which is then converted to product. This transition state or activated complex is unstable. This can be represented by a simple graph. I am first drawing graph for elementary reaction. Elementary reaction means reaction takes place in single step. If a reaction takes place in single step, that is known as elementary reaction. Reactant molecules collide each other to form activated complex, which is then converted to product. Formation of activated complex is not a step. It is the part of step. Reactant is converted to product through activated complex. So formation of activated is not a step. The graph between energy and reaction coordinate. Reactant molecules have this energy. Consider. Reactant molecules have this energy. If they collide each other, it form activated complex which is unstable. Unstable substance have very higher energy. It is activated complex. This activated complex is then converted to product. The product may have energy greater than reactant or less than reactant. First I am considering the energy of product is less than reactant. So the reaction path can be represented as reactant is converted to activated complex. That activated complex is converted to product. So with the energy of reactant, it cannot be activated complex. So it requires an additional energy. That additional energy is known as activation energy. That is EA. Activation energy have a unit joule per mole. So this is the additional energy required for reactant molecules, that is joule per mole. This energy is gained by collision between molecules. So this additional energy is attained by collision between molecules. It is the energy of reactant that have first. It is the additional energy required for the reaction. So the total energy can be represented as ET. This ET is known as threshold energy. Threshold energy is the minimum energy that reactant molecules should have at the time of reaction. This ET is the sum of energy of reactant molecules and its activation energy. threshold energy is the sum of energy of reactant and activation energy. We have to point out one more thing. It is the energy of reactant, it is the energy of product. So there is a change in energy during reaction that can be represented by this term. That energy is delta H. What is delta H? That is reaction enthalpy. So in this graph there are three terms: EA activation energy, ET threshold energy, delta H, that is reaction enthalpy. Okay, now I am going to draw this same type of graph in complex reaction. Complex reaction means multi-step reaction. So the reaction involves more than one step. Consider a reaction. A plus B become C. If it involves two steps, first step is this A and B combine to form I. I is intermediate. In second step, that intermediate is converted to product. So we are using a term intermediate. Intermediate and activated complex are different. Formation of intermediate is one step. That intermediate is converted to product is another step. So this can be drawn by the graph. The same graph between energy and reaction coordinate. Reactant molecules combine together to form intermediate in one step. That intermediate is transferred to product in another step. So we have to check the speed of reaction. Consider formation of intermediate is slow step and conversion of intermediate to product is fast step. In most of the case, formation of intermediate will be slow step. The opposite can also possible, but in most of the case, formation of intermediate is slow step. Conversion of intermediate to product will be fast step. So the graph can be reactant is converted to intermediate in one step. That intermediate is converted to product in another step. This type of graph can be drawn for complex reaction. First step, reactant is converted to intermediate through activated complex. So in one step there is one activated complex. In second step, intermediate is transferred to product through another activated complex. So in complex reaction, intermediate and activated complex are present. Activated complex and intermediate are different. What is activated complex? It is the transition state through one. It is the transition state formed during one step. But intermediate is the substance which can be separated after one step. But that intermediate also less stable. So this is converted to product. First step is slow step. That means first step have very high activation energy. It is EA1. Second step is slow step. It have very low activation energy. So EA1 very greater than EA2. That means step 1 is slower than step 2. So, if the step 1 is faster than step 2, the graph will be just reversed. So, in this graph, step 1 is slow, step 2 is fast. So, step 1 have higher activation energy than step 2. In this reaction also, we can mention delta H, enthalpy change. That is the energy difference between reactant and product. Let's apply this Arrhenius theory in reversible reaction. Reversible reaction means reactant is converted to product and product is converted to reactant. These both reactions are carried out through same activated complex. So reactant is converted to product through one activated complex. Product is converted to reactant through same activated complex. When we are discussing this graph, let's compare endothermic process and exothermic process. Very simple comparison. In reversible reaction, endothermic and exothermic. We are drawing the same graph between energy and reaction coordinate. Reactant is converted to product through activated complex, but it is endothermic process. Endothermic process means energy is absorbed during reaction. So, energy of product will be greater than energy of reactant. We know this state is activated complex. What will be activation energy of this reaction? That is, we know, E. This is activation energy of forward reaction. So, I am representing as EF. Let's consider backward reaction. What is the conversion of product to reactant through same activated complex? So, this is activation energy of backward reaction. Okay. In this graph also, we can simply mention delta H. In endothermic process, forward activation energy is greater than backward activation energy. EF greater than EB. And since energy of product greater than energy of reactant, delta H is positive. This we know in thermodynamics. This about endothermic reaction. Let's check exothermic reaction graph. Very simple. The graph between energy and reaction coordinate. This is energy of reactant. Energy of product should be less than energy of reactant. Why? It is exothermic reaction, that is energy is released. This we know activated complex. Okay. In this graph, forward reaction is conversion of reactant to product. So this is energy of activation energy of forward reaction. Conversion of product to reactant is backward reaction. Its activation energy is this. Very simple. In this case, backward reaction have higher activation energy than forward. EB greater than EF. Since energy of product less than energy of reactant, delta H equal to negative. Okay. In this case, delta H can be calculated. It is the difference between EF and EB. In exothermic reaction, delta H is represented this term. This delta H is also difference between EF and EB. Whether it is endothermic or exothermic reaction, delta H is energy of forward minus energy of backward. This equation is common for endothermic and exothermic reaction. In endothermic reaction, EF greater than EB, so delta H will be positive. In exothermic reaction, EB greater than EF, so delta H will be negative. By Arrhenius diagram, we can explain effect of catalyst. We know catalyst generally alters rate of reaction. That means it can increase or decrease rate of reaction. But generally catalyst is used to increase rate of reaction. This effect of catalyst can be explained by Arrhenius diagram. It is very simple. Graph between energy and reaction coordinate. Graph between reactant, the conversion of reactant to product through activated complex. Consider this graph is for uncatalyzed reaction. That means without catalyst. This reaction have activation energy EA. EA is the activation energy of this reaction. If catalyst is added to this reaction, what will happen? This catalyst changes reaction path by forming new activated complex. So this is the new activated complex formed. Then what will be the path of reaction? This reactant is converted to product through this activated complex. Now what will be the activation energy of this reaction? That is EA. This reaction is for catalyzed reaction. Uncatalyzed reaction have higher activation energy. Catalyzed reaction have lower activation energy. So catalyst decrease activation energy to increase rate of reaction. Catalyst decrease activation energy to increase rate of reaction. In catalyzed reaction and uncatalyzed reaction, delta H still remains same. That means catalyst cannot change enthalpy of reaction. So catalyst changes activation energy, but it do not change delta H of the reaction. We are familiar with the Arrhenius equation. Arrhenius equation is the relation between rate constant and temperature. Rate constant K equal to A, that is Arrhenius constant, E raised to minus EA by RT, EA activation energy, R universal gas constant, T absolute temperature, that is temperature in Kelvin. It have another form. If you are using natural log K, that means log to the base E, ln K equal to minus EA by RT plus ln A. If you are using log K, that is common log to the base 10, log K equal to minus EA by 2.03 RT plus log A. At a different temperature, rate constant can be calculated by this equation. log K2 by K1 equal to EA by 2.03 or T2 minus T1 by T1 T2. In this equation, e raised to minus EA by RT is known as fraction of molecules having activation energy. That is, this value is the fraction of molecules having activation energy. This value is known as Boltzmann factor, not Boltzmann constant. It is known as Boltzmann factor. By this equation, we can relate the effect of temperature and effect of catalyst on rate of reaction. That are the important points we have to focus. These are the general area everyone know very. Okay, let's check effect of temperature and effect of catalyst on rate of reaction. As temperature increase, we know EA by RT decrease. So, minus EA by RT increase. That is E raised to minus EA by RT increase. K increase. If K increase, rate of reaction increase. So, as temperature increase, rate of reaction increase. It can be compared by Arrhenius equation. When catalyst is added, EA decrease, then what will happen? EA by RT decrease. So, minus EA by RT increase. E raised to minus EA by RT increase. K increase. K increase means rate of reaction increase. So, effect of temperature and effect of catalyst can be explained by Arrhenius equation. We have to focus the point, when temperature changes, EA remains same. When temperature changes, EA remains same, but when catalyst added, EA decrease. So, as change in temperature, EA do not change, but when catalyst is added, EA changes. But as temperature increase, rate increase. When catalyst added, rate increase. Let's discuss four graph, that is natural log K and 1 by T, common log K and 1 by T, K and 1 by T, K and T. We know the relation between ln K, that is ln K equal to minus EA by RT plus ln A. So, if we draw the graph between ln K and 1 by T, the graph will be like this. Its y-intercept will be ln A and slope will be minus EA by R. So, graph between ln K and 1 by T, graph like this, having y-intercept ln A and slope minus EA by R. So, what is the relation between log K and 1 by T? Log K equal to minus EA by 2.303 RT plus log A. So, the graph between log K and 1 by T will be in the same manner. But the y-intercept is log A and slope is minus EA by 2.303 R. So, the pattern of graph same, but y-intercept natural log A, it is common log A. Slope minus EA by R, slope minus EA by 2.03R. If we draw the graph between K and 1 by T, we know as temperature increase, K increase. So as 1 by T increase, K will decrease like this. So what will be the graph between K and T? As temperature increase, K increase. So the graph will be like this. This graph is exponential graph. Exponential relation. So these are the 4 graphs we have to know in Arrhenius equation. From the above graph, we have to determine definition of A. Very simple. If 1 by T equal to 0, temperature is infinity. At that time, ln K become ln A. That is K become A. When temperature is infinity, K have maximum value. Why? As temperature increase, K increase. So we can define A like this. Arrhenius constant is the maximum rate constant of reaction when temperature is infinity. The definition is Arrhenius constant is the maximum rate constant of reaction when temperature is infinity. So unit of Arrhenius constant will be unit of rate constant. Unit of Arrhenius constant will be unit of rate constant. Now we have to check effect of temperature on rate of reaction based on EA value. Generally, activation energy of reaction will be in the range 52 to 53 kilojoule per mole. So, rate of reaction will be doubled for every 10 degrees Celsius increase or 10 Kelvin increase. Both are same because it is change in temperature. We have this statement, rate of reaction will be doubled for every 10 degrees Celsius increase or 10 Kelvin increase. This is possible only if EA is in the range 52 to 53 kilojoule per mole, but in most of the reaction, these are the value of EA, so we can have this statement. But we have to focus two statements also. If activation energy of reaction is 0, that is a hypothetical condition. If EA equal to 0, then temperature have no effect on rate of reaction. That means if temperature increase, rate of reaction remains same. If EA equal to 0. Another statement, higher the value of EA for a reaction, effect of temperature on rate of reaction also increase. So higher the value of EA, effect of temperature also increase. If EA equal to 0, temperature have no effect. If EA equal to 52 to 53 kilojoule per mole, rate will be doubled for every 10 degrees Celsius increase or 10 Kelvin increase.